Hello and welcome to the Week 6 review for Math 2414. In this review, we're going to be covering some area of surface revolution, which we didn't get to last week, as well as some differential equations and Euler's method. So let's go ahead and get started. So first off, let's talk about area of surface of revolution. Last time we talked about arc length, and area of surface of revolution is really just kind of an extension of that. So let's see if we can grasp some of the intuition behind it before jumping right in. So when we have a cylinder and we want to define the surface area of that cylinder, ignoring the ends, well, what we can do is we can take the length of that cylinder and multiply it by the circumference of one or of the cylinders. So in other words, we can find our surface area just by taking that circumference, which is 2 pi times the radius, and multiplying it by the length. Now, this doesn't change even when we have somewhat weirder shapes. So if we had a shape that looked kind of like this, where our radius is changing, well, we can still find the area by performing 2 pi times the radius times the length. In this case, though, all that's changing is the radius. We don't have a fixed radius anymore. So when we have some kind of shape or some kind of curve, let's say like this, and we rotate it about the x-axis, well, suddenly we end up with one of these weird looking shapes. And we're interested in finding the surface area. And as it turns out, the surface area is still exactly equal to 2 pi times the radius times the length. Right. So in this case, our radius is the distance from the center up until the arc. And that is exactly our function value f of x. So we can go ahead and put f of x in our integral. We also have our 2 pi. And we already have an equation for the arc length. The arc length would be our integral, 1 plus f prime of x squared. And this is our formula for our volume by surface of revolution. This is for rotation about the x-axis. If instead we were doing rotation about the y-axis, here I'll make a note, rotation about x-axis. If we're going about the y-axis, the only thing that changes is instead we now have our radius is simply this distance here, which is just x. So let's see if I can, oh dear. This one is not as good of a picture, unfortunately, but you get the idea. In this case, our arc length would be x times 2 pi. So in this case, when rotating about the x-axis, our radius is f of x. When rotating about the y-axis, our radius is simply x. And our arc length is, of course, the same. So let's go ahead and do a couple of example problems. Let's say we wanted to find the surface area of a cone. with no base? Well, we can represent a cone by taking a line through the origin, that line being y is equal to kx, where k is just some slope constant. So we take that constant, and then we rotate it about the x-axis, like so, and this will get us some kind of cone. So we know that this distance here would be the height of our cone as well, which means that the area of our cone, or the surface area of our cone, is equal to the integral from 0 up until h of 2 pi times f of x, which is kx, times the square root of 1 plus f prime squared. In this case, y is equal to kx, so the derivative is just k. And since k is a constant, it doesn't make too much of a difference. Now, evaluating our integral, the only non-constant term is just this x here. So this integral simplifies to k root 1 plus k squared times pi times x squared, ranging from 0 up until h, which gives us k square root 1 plus k squared times pi times h squared. Now, if we interpret what k is in terms of a cone, well, k in this case is our slope. And slope is equal to rise over run. Rise, oh dear, oh my goodness, one moment. Our k is equal to rise over run. In this case, our run is equal to h. And our rise is equal to the radius. So k is equal to r over h, which implies, if we replace all the k's in this equation, we get that our surface area is equal to r over h root 1 plus r squared over h squared times pi times h squared. And I don't want to have fractions inside my square root, so I am going to multiply some things out, and I get that surface area is equal to, now I'm left with r over h squared square root h squared plus r squared. So the simplification I'm doing here is I'm saying 1 plus r squared over h squared can be rewritten as h squared plus r squared over h squared, which is equal to 1 over h square root h squared plus r squared. And then I combine this 1 over h here with this h here to get my h squared there. And then I have pi times h squared, and of course this h squared is going to cancel with this h squared. So my surface area is equal to r times pi times the square root of h squared plus r squared. And this is a formula for the surface area of a cone without the base. All right. For another practice problem, let's take a look at the surface area of square root 1 minus x squared rotated about the x-axis on the interval from -1 up into +1. Well, we can simply set up our integral we have 2 pi times, because it's around the x-axis, we want to rotate it, we want to multiply by f of x, so 1 minus x squared times the square root of 1 plus our derivative squared. In this case, our derivative is, here we need to use the chain rule, 1/2 times 1 minus x squared to the negative 1/2, so 1 over square root 1 minus x squared, times the derivative of the inside, so times negative 2x. And we can simplify this to negative x over square root 1 minus x squared, like so. Okay. And then we need to square this term, and that gets us x squared over 1 minus x squared. Now we just need to simplify this integral wherever possible. Again, I don't like having fractions inside my square root, so I'm going to simplify using a similar method. I'm going to say that 1 plus x squared over 1 minus x squared is equal to 1 minus x squared plus x squared over 1 minus x squared. So I'm just finding a common denominator, which is 1 minus x squared. And my negative x squared here is going to cancel with my positive x squared, and that leaves me with a 1 over 1 minus x squared. Now when I continue to simplify, here I have square root 1 minus x squared. This actually turns into, I can take the square root of the top and the bottom individually. The square root of 1 is just 1, and then I have 1 over square root 1 minus x squared. Now I have 1 minus x squared times 1 over 1 minus x squared, and that cancels. And this integral is simply 2 pi x evaluated from negative 1 to positive 1. And that is 2 pi minus negative 2 pi, or 4 pi. All right, so that is our final answer. And this actually matches what we were thinking, what we thought it should match, because if we look at our original equation, this is the equation of a circle. So a circle specifically with radius 1. And we happen to know that when we rotate a circle of radius 1 about the origin, that becomes a sphere of radius 1. And we have a formula for the surface area of sphere. The surface area of a sphere is 4 pi r cubed. And, is 4 pi r squared. And in this case, because our radius is 1, our surface area would equal 4 pi times 1, which is, of course, 4 pi. So this does match what we already know. All right, so that's it for surface area. We'll go ahead and move on to taking a look at some differential equations. So differential equations are essentially just ways that we can model a lot of different things. So one common example is taking a look at population growth. If we wanted to look at population growth, well, we could say the change in population with respect to time is equal to some rate constant times the current population. In other words, the larger the population is, the faster the population is going to grow. Now, if we wanted to solve this differential equation, we want to use a method that's often called separate and integrate, we're going to put all the things with a p on one side and all the things with a t on the other side, and we get dp over p is equal to k dt. Now integrating both sides of this, we get that the natural log of p is equal to kt plus c. So e to the natural log of p, which is p, is equal to e to the kt plus c, which is equal to c1 e to the kt. So our solution is p is equal to c1 e to the kt. And that would be a solution to our differential equation. But the main takeaway here is that our differential equation is often easier to write than this final answer. It's often easier to come up with an expression for the rate of something rather than just a closed form expression for the population at any given time. Now, if you wanted to look, the main issue with this model for population is it assumes that the population can grow as much as it needs to, right? So in this one, when we have a larger p, our rate of change of population is going to be larger. In other words, the bigger the population is, the faster it grows. But that's not necessarily always the case. Sometimes our population hits a limit. So this is often called unbounded population growth. And we actually have a whole different formula for bounded population growth. The differential equation for a bounded population growth is equal to Kp times 1 minus P over M. And the number M is often called the carrying capacity or the maximum population, because as soon as P is equal to M, well then P over M is equal to 1, so 1 minus P over M is 0, and our population, our dP over dt, or rate of population change, is 0 as well. Now the solution to this one is a bit more difficult, so I'm not going to go in depth, but there are a couple of things you should realize. There are 2 occasions with this bounded population model where we have dP over dt equals 0. And that's when P is equal to 0. So if we don't have anyone in our population, it obviously can't grow. Or when P is equal to M, then we'll have 1 minus 1, and which gets to 0, like I stated earlier. And these mean that we'll never get out of this situation where dP over dt is 0. And because of this, because they result in our population never changing, we call them equilibrium solutions. In other words, if they keep our equation and our numbers all constant, we'll call them an equilibrium solution. So let's go ahead and do another example of solving a differential equation. Actually, we'll clarify a few things. Just say, in general, a differential equation has the form y prime is equal to a function of x and y. So in the past, you've usually seen things where your derivative is a function of just x. In a differential equation, though, we often allow the slope to be defined based on y as well. And this is actually really useful because it gives us a lot more flexibility in how we define our slope. So one thing you might see is like y prime is equal to x times y. That's a differential equation. Now let's go ahead and take another look. So, apologies. So let's do a quick example. Suppose we have this formula or this function y is equal to negative t cosine of t minus t. Well, I say that it's a solution to the equation t dy dt is equal to y plus t squared sine of t. And in order to check this, all I need to do is I know what y is, I don't know what dy dt is, so I need to find dy dt. And to do that, I just differentiate both sides of this equation. First, I use the product rule. And then I simply plug everything that I know into this equation here. So t times dy dt is equal to y plus t squared sine of t. And then I can go ahead and distribute, and I get negative t cosine of t plus t squared sine of t plus t is equal to negative t cosine of t minus t plus t squared sine of t. And these two things are obviously the same, so this equation here is a solution to my differential equation. And that's just a way of verifying that a solution is correct. All right. Go ahead and try your hand at solving the differential equation y prime is equal to xy cubed, where we have an initial condition y of 0 is equal to 2. And just as some hints, you're going to want to separate and integrate for this one. And this y of 0 is equal to 2 should be used to solve for your c value. And also see if you can show that y is equal to 1 over square root c minus x squared, where c is a constant, is a solution to y prime is equal to xy cubed. So go ahead and take a few minutes to work those out, and we'll go over them in a couple minutes. All right, let's go ahead and go over these problems. So in the first one, we're going to want to separate and integrate. So in this case, we get y prime over y cubed is equal to x. And integrating both sides of this, we get that negative 1 over 2y squared is equal to 1/2 x squared plus c. Now this means we can cancel our 1/2s and we get negative 1 over y squared is equal to x squared plus c1. So we can multiply both sides by y squared and divide both sides by x squared plus c1. And we get negative 1 over x squared plus c1 is equal to y squared. So in this case, because we have that y of 0 is equal to 2, this means that negative 1 over 0 plus c1 is equal to 2 squared. So this means that negative 1 over c1 is equal to 4. So we have that c1 is equal to negative 1/4. And as a result, we have the solution y squared is equal to negative 1 over x squared minus 1/4. And you'll have to note that this equation is only valid on a very specific domain because y squared is always positive. So on this right-hand side, we need to make sure that this right-hand side is always positive as well, which means that x squared minus 1/4 has to be negative to cancel out this negative up here. So x squared minus 1/4 should be negative. Because x squared is always positive, we need to make sure that x squared is smaller than 1/4. So solving our differential equation kind of introduces this domain restriction here. All right. Cool. Moving on. Now, in this problem, we need to first find what y prime is. And this isn't terribly difficult. We can just use the chain rule. We get negative 1/2 times 1 over square root c minus x squared. Actually, I should do this in a way that's probably a little more apparent what I'm doing. So we have, using the chain rule, c minus x squared to the negative 1/2. We take that, c minus x squared, negative 1/2 is the power, it goes out front. Then we decrease the exponent by 1 and multiply by the inside, or the derivative of the inside, sorry. Here, negative 2 cancels with negative 1/2 completely, including the negatives both canceling. So our derivative, y prime, is equal to x over c minus x squared to the 3/2. And now we can substitute everything we know into our differential equation. So we have x over c minus x squared to the 3/2 is equal to x times 1 over square root c minus x squared cubed, which is, of course, x over c minus x squared to the 3/2. And clearly these both match. So we have that this is a solution. All right. I think that's basically it for differential equations. So now let's move on to talking about some slope fields. Now, slope fields are really useful in terms because they let us visualize differential equations. So let me see if I can actually just find a picture of a slope field really quick. So I can kind of show you what it looks like. Here we go. And there we go. Now let's see if I can make that a little bigger and move it over here. So here we have a slope field, and the idea behind a slope field is at each little tick mark, so let's say right here, you can see we've got a tick mark right there. The idea is you can take a look at that and see the slope at that particular point. And what this lets us do is it lets us sketch out complete curves of individual solutions to our differential equation. So this is one particular solution. In other words, a solution with one particular c value of our differential equation. Here's another, and it's essentially just a line following a specific set of tick marks. So we could even, if we so chose, draw in a couple of our own solutions, where here we've got a tick mark pointing up, and we can see that it keeps going up, and our slope slowly decreases the further over we get. So that would be another solution. Or we could draw in another where our slope initially starts off very steep, but slowly tapers off as we get closer to this horizontal asymptote here, and so on. So the idea behind a slope field is it helps with sketching our solutions, and it also lets us visualize a lot of different solutions to our differential equation all at once. They could be used a little, actually never mind. Basically, slope fields can be useful. They're not necessarily used a ton, but when they are used, they can be pretty powerful. Also, they're pretty to look at, so there's that too. Okay, and now let's talk about Euler's method. So Euler's method approximates differential equation solutions, because sometimes it is difficult to get an exact solution. And the idea is we can approximate a smooth curve. So if we have like a curve that looks something like this, we can approximate it starting at one point by taking a series of tangent line approximations and following those along, because it's pretty easy to come up with a tangent line approximation. So we can use those to kind of stay pretty close to our actual solution. Now what this ends up looking like is something like this. Let's go ahead and do an example. If we had the differential equation y prime is equal to x plus y, and we also knew that our starting value is equal to 1, and we were wanting to know what y of 3/5 was, using 3 of these increments, which we'll call steps. Well, we could start off, we already know that y of 0 is equal to 1. Oops. Which means we can make a tangent line approximation for y of 1/5 by saying that y of 1/5 is about equal to, well, we take our starting value 1, then we add whatever we think, and then we just need to add essentially the rise over the run, the slope multiplied by the distance over we go, because that'll get us our change in y. The slope multiplied by the distance we go should get us our change in y. In this case, our slope is our y prime, so x plus y. Here, our x is 0, our y is 1, so 0 plus 1 is 1, and our y is, and our distance we go over is 1/5, or 1/5 minus 0 is 1/5. And this gets us 6/5. Next, we need to approximate y of 2/5. And our starting value that we start from now is our previous one, 6/5. Then we add our slope times our distance over ego. Again, our distance over ego is going to be 1/5 because we're stepping from 1/5 over to 2/5. The distance between that is 1/5. And our slope is again y prime. So y prime is x plus y. Our x value is approximately 6/5. Our y value is 1/5. So, I'm sorry, our y value is 6/5. Our x value is 1/5. 1/5 plus 6/5 is 7/5. And this will get us a value of, because I computed it in advance, 37 over 25. Finally, our final value, y of 3/5, is approximately equal to our previous y value at y of 2/5 plus our slope, in this case x plus y again, so 37 over 25 plus 6/5 times the distance over ego, which is 1/5. And I'm not going to bother simplifying this, but this should be not a 6/5. This should be, oh come on, I'm trying to select the eraser. There we go. Again, our slope should be our x value plus our y value. No, I just want to select the pin. Let's see, why is this glitching on me? Give me one moment. All right, there we go. So as I was saying, I made a slight mistake here. My slope should have been the previous y value plus the previous x value. In this case, 37 over 25 plus 2/5, not 6/5. But this would be our final answer for our slope. All right, we'll go ahead and do a quick practice problem for Euler's method. Suppose that your differential equation was fairly simple. Simply y prime was equal to y, and your initial value was equal to 2. Approximate y of 1 using 3 steps. I'll give you a few minutes to work through that. Good luck. All right, let's go ahead and go over this one. So first off, you already know that our first value is 2. So using 3 steps, we're going from 0 to 1. So each step size would be 1 minus 0 divided by 3, or 1/3. So our first step would be at x equals 1/3. And we can say that at x equals 1/3, our y value is approximately our old y value plus our slope times our change in x. So our change in x is 1/3, and our slope is simply our previous y value, or 2. And 2 plus 2/3 is 8/3. Next, we have y of 2/3, which would be our previous y value, 8/3, plus our change in x, 1/3, times our previous y value, which is our slope, because our slope is just our y value. So times 8/3, and this comes out to 32/9. And finally, we have our approximation for when x is equal to 1, and that would be our previous y value, 32/9, plus 1/3 times our slope, which is our y value, 32/9. And this evaluates to 128/7. So this would be our approximation for y of 1. All right, anyway, that's all I've got for you today. Thank you for coming in, and have a nice week.